A special form of a diffraction grating is a polarizer. Polarizers have very, very small slits in them, and it's a diffraction grating that um, with these slits very close to each other. And here we're just illustrating it with a rope or a string. If I have the wave coming in so that it is in line with the slit, then the wave continues through the slit. But if I turn the wave so that it's going through the narrow part of the slit, then I'm getting a block, and on the other side it doesn't come out as a wave. Now we can look at it from the electric field standpoint here, and we see that with the electric field, dependent upon how this angle is, of course electric fields can be oriented in all sorts of different ways. But notice that as the light goes through, if this was a perfect diffraction grating with a perfect polarizer, then all of this wave here that's not vertical would get blocked, and the only one that would survive would be the vertical part, or the vertical waves. And if I take and I have waves in both directions, so I have waves that are vertical, some that are horizontal, then after the first polarizer, if it's vertically oriented, all I have are vertical waves. And through the second polarizer, if it's 90 degrees, it's got a horizontal axis, then I would get no light on the back side. Now realize that polarizers are not perfect. Are not perfect. And so you're going to get a little bit of light, because it's going to allow some of these very closely oriented electric fields to go through on both sides. So they're not perfect. They will allow a little bit to go through, but the more lines you have, the better they're going to be. So if we look here, if I take and go through the first polarizer, about 1/2 of the intensity is done away with. So if this first polarizer, my intensity is I0, and this is my intensity after the first polarizer, then my intensity in region 1 here after the first polarizer is going to be equal to 1/2 of the original. Now, as I keep adding polarizers, it becomes an iterative calculation. And so, because now I have these polarizers and the angles of these slits can be varied between 0 and 90 degrees, then my next polarizer intensity is going to equal the previous polarizer intensity times cosine squared theta. So all I need to know is the orientation of the angle between each of the polarizers, and I can work my way through iteratively to get to the intensities at the end. In this case, because it's 90 degrees, the cosine of 90 is 0, and square that, that's 0, so I get, in this case, intensity of 0. But this angle could be any angle dependent upon the way the polarizers are oriented. Now let's do an example. We want to know what angle should the axis of two polarides be placed so as to reduce the intensity of the incident unpolarized light to 1/3 and to 1/10. So we have I1 is equal to 1/2 I naught, and for the second one we have I2 is equal to I1 cosine squared theta, but I1 is just equal to 1/2 I naught cosine squared theta. And now I can solve for theta, so I have cosine squared theta is equal to 2I2 over I naught. Cosine of theta is equal to the square root of 2I2 over I naught. But I2 over I naught is just the ratio that I'm looking for. And this ratio is either the 1/3 or the 1/10. So theta is going to be the arc cosine, the square root of 2 times my ratio. So for 1/3, it's cosine, or arc cosine, square root of 2 times 1/3, and that's equal to 35.264 degrees. So that's the offset of the angle between the two polarizers. And theta for 1/10 is equal to the arc cosine square root 2 times 1/10, and that's going to be equal to 63.435 degrees. So the biggest thing to remember is that it's 1/2 after the first polarizer. The intensity is 1/2, and then after that you have to go through this iterative process to get to the correct angle that you're looking for.